What I'm going to do today is continue our discussion of the jellium model, which you may recall is just the simplest model of a metal where you have electrons moving on the uniform positive background representing the ions. Before I go ahead, let me make a small correction. I think in my last lecture, when I wrote the Hamiltonian, second quantized Hamiltonian, in terms of field operators, I had these two terms switched. In this case, it's not OK because this t here is a differential operator which has this Laplace in it, and it should only act on the second field operator, so they don't commute. And if you have this in your notes, can you please make that correction? In the second term, in the potential term, the ordering doesn't really matter between the kernel and the operators because there the kernel is just a scalar function, and it commutes with the operators. In this case, it does not. So the ordering has to be like there. So anyway, with this correction, last time we were developing this jellium model by taking a first quantized Hamiltonian describing that situation and rewriting it in second quantized form. And this is the place where we stopped. So let me remind you what this is. This is just the kinetic energy, which tells you that basically this is the number operator here, which gives you the number of electrons with momentum k and spin lambda. And it tells you that each such occupied state has energy, kinetic energy, just h bar squared k squared over 2m, just like a free particle. And the second term comes from interactions. And we still have to deal with this issue of this mu. Remember, we used screened Coulomb or Yukawa interaction because individual terms would be divergent with straight Coulomb. And we see that indeed this term, which comes from the background, would be infinite if we took mu to 0. But we will see how this cancels against the term that comes from this part. This is the electron-electron interaction, and we will comment on it as we go along, exactly what it does. Are there any questions from anything that we discussed previously? If not, let's just proceed. So what we want to do once again is to resolve this divergence when mu goes to 0. And for this, let us manipulate a little bit this interaction term so that we can write it in a more transparent way. So what we see here that there is 4 different summations over momenta and spin, but there's 2 Kronecker deltas for spin and 1 for momenta. These basically represent spin conservation. These represent momentum conservation in the interaction term. So let us rewrite this term in such a way that these conservation laws are more obvious. And to this end, let's introduce new variables. And we do it as follows. We replace k1 with new variables k plus q, k2 with p minus q, k3 will be equal to k, and k4 will be equal to p. And similarly, we call alpha lambda 1, which is through this Kronecker delta also equal to lambda 3, and beta we call lambda 2, which is through this Kronecker delta equal to lambda 4. So we're replacing 4 momenta, k1, k2, k3, and k4, with just 3 momenta, k, p, and q, in such a way that this momentum conservation is automatically obeyed, right? You go from two momenta k and p to two momenta k plus q, p minus q, but their sum is the same, because when you add k1 plus k2, the q drops out, and therefore this momentum conservation is implicitly taken care of in those variables. So let us rewrite just the interaction term here in terms of those new variables. I will move this a little higher. So I'm just rewriting the interaction term, this one here. The first one remains the same in those variables, and it simplifies like this. Okay, so I have eliminated these Kronecker deltas, and I only now have a summation over 3 momenta and 2 spin variables reflecting those conservation laws. Okay, now when I look at this expression, I furthermore see the following property. If I try to send mu to 0, the only place where here it will lead to a divergence is the term in which q is equal to 0. Okay? Whenever q is non-zero, I can safely send this parameter to 0, and this term will remain finite, so I can do that. But in the term when q is equal to 0, that would lead to an infinity, so I have to single out that term and treat it separately. For that reason, I will rewrite this in the following way. E over 2v sum. So in the limit, let me write it like this. In the limit mu goes to 0, I can write it like this. K, P, Q. And I put a prime here and alpha beta 4 pi over q squared. And I just copy everything else. C dagger k plus q, alpha c dagger p minus q, beta c p beta ck alpha. And what this q means, this q stands for an instruction to omit q equals 0 term. Okay, but of course I have to now add that term that I omitted. So I write this as follows: sum over kp alpha beta 4 pi over mu squared c dagger k alpha c p beta c p beta ck alpha. Okay, so once again in this term, since I'm omitting q equals 0, I already took my mu to 0, and this term is well defined in that limit. In this term here, this is just what's left after this. This is just basically q equals 0 term of that sum, and I explicitly took that into account here. And mu sits there, and that term would be divergent, so I have to look at it more carefully. Okay. So what I see here is that basically these two guys and these two guys will form a just a number operator. When I combine them, all I need to do is to commute this ck alpha through these two so that it's next to its partner here, and then I can write this in terms of just a number operator. So let me do that. And that will lead to further simplification. So I'm just now focusing on this term and rewriting it like this. E squared over 2v. I take out 4 pi over mu squared. That's just a constant. And then I still have to sum over kp alpha beta. And this commutator does the following. C dagger k alpha, ck alpha, c dagger p beta, c p beta, minus delta kp delta alpha beta. So what I have done, I first commute these two guys, right? But here I just incur an overall minus sign, okay? And then when I'm commuting this one through that one, I incur, in addition, this right-hand side when indices k and p and alpha beta are the same, just using the standard fermionic anti-commutation rules, okay? Now I can perform this summation. For instance, if I just combine this term with that one, all I get is a sum over k and alpha of this. And remember, when I combine these two operators, this is nothing but the number operator. Similarly, this is nothing but the number operator like this. So when I perform that sum, this is simply e squared over 2v, 4 pi over mu squared. I'm just copying this n times n minus 1, where this capital N is the total number of electrons operator. Okay. Now, why is this useful? This is useful. Rewriting it in this way is useful because total number of electrons in a system is a good quantum number, right? My n operator actually commutes with the Hamiltonian. Or you can call it a conserved quantity. To see this, well, one can either formally perform that commutator, which is not a difficult thing to do, but I will not do that here in class. It's somewhat laborious. But one can very simply argue that this is the case just by looking at the Hamiltonian. You see, if I look at the kinetic energy piece, it obviously does not change the number of electrons in the system because it annihilates one and then it recreates it immediately, right? So if I act with it on a state with n electrons, what comes out is also a state of n electrons. And similarly here, I annihilate 2 electrons and then I recreate them in different momentum states, and that does not change the total number of electrons in the system, which is to say that momentum is momentum is also a good quantum number, but that's not the point. The number of electrons is a conserved quantity in the system, and therefore I can replace n with its eigenvalue, which is just the number of electrons in the system. Is that clear, or are there any questions? OK, but you see, this is not bad, because once I replace n hat in there with just n, then I can see that part of it, at least, will cancel against that divergent term up there in the first line. Question?
If you were in a one-particle state, and then you apply 2 happens, what do you think is going to happen?
Well, then you don't get a state in Hilbert space. You just get 0, right?
Right.
So you just get out of the Hilbert space. So it's not that you're changing the number of particles.
Okay, the Hilbert space is just 0, right?
Yeah, and 0 is not really a normalized vector in Hilbert space, or normalizable vector in Hilbert space, right? Yeah. So yeah. So let's just put it this way: whenever you act with the Hamiltonian on a vector in a Hilbert space, and you get a valid vector in the Hilbert space back, that will represent a state with the same number of electrons. If you get 0, then you're just out of Hilbert space, and that question doesn't really arise. Any other questions? Okay, so let's just combine everything that we have, and let's now combine all this C number. Okay, what is it that I want to say? So let's now replace n hat with n and combine it with that term. So what we have is e squared over 2 n squared over v 4 pi over mu squared minus e squared over 2 n over v 4 pi over mu squared. So this is the contribution from there, right, where I just expanded everything. And then I add to it contribution from the background, which is minus e squared over v n squared over v 4 pi over mu squared. And I see that happily these two terms exactly cancel. Somewhat unhappily, I'm still left with this term, which nominally looks like it is divergent and the mu goes to 0 limit. However, as we discussed at the beginning, what I want to go to thermodynamic limit, which is n v goes to infinity while n over v equals n stays constant. And in thermodynamic limit, what I'm going to be looking at is energy per particle in the system rather than the total system energy, because total system energy in infinite system would clearly diverge. So a meaningful quantity to look at is Hamiltonian divided by n. And this term here would contribute. So there's all these terms that have operators in them, but the scalar term that I get from here is minus e squared over 2, 1 over v, 4 pi over mu squared. And in thermodynamic limit, this also goes to 0, whereas all these other terms, as we will see, will go to some finite value. So in other words, when I study energy per particle in the thermodynamic limit, all these terms with operators in them, they will give me some non-zero value, whereas this term that I'm dealing with will just go to 0 when I send volume to infinity. So from now on, I will just neglect that. And in thermodynamic limit, indeed, I can take this parameter to 0 and end up with Hamiltonian that is divergence-free. So let me just summarize and write the final expression for this Hamiltonian. And let me put a little frame around this. So this is the final Hamiltonian of coulombically interacting electrons on the background of a positive charge question. Okay. So once again, the meaning of the first term hopefully is clear. It just says that every occupied state, every state for which this number operator is 1, contributes kinetic energy that is proportional to momentum squared. That should be intuitively clear. The second term comes from Coulomb-Coulomb interaction and can be represented, if you like diagrams, can be represented as follows. You have two electrons that come in with momenta k and p. Then there is an interaction vertex whose value is 4 pi over, it should be q squared, sorry, 4 pi over q squared. So they come in, meaning they are annihilated in this process, and out come two electrons with momenta k. Sorry, let's do this. P minus q and k plus q. So in particular, momentum is conserved in these processes, which fundamentally comes from the fact that the original Hamiltonian was translationally invariant. And for those of you who studied quantum electrodynamics, this is corresponding to the Feynman diagram that you looked at in quantum electrodynamics, where in that case this would be a photon that mediates that Coulomb interaction. But of course, in condensed matter physics, since we're concerned with non-relativistic behavior of particles, we can represent this photon by an instantaneous interaction, and therefore we just have a simple vertex like this. There's no retardation effect that would result from the finite time that it takes for this photon to propagate, because basically we're looking at electrons moving at subrelativistic speeds. Okay? Any questions about this? Yes?
Can we see that the Feynman diagram you described is corresponding to this picture we have?
It's corresponding to what?
To this picture we have.
Can we see that these two diagrams correspond to one another? Well, I don't know how else would you like to see that. I'm just drawing this analogy, right? Okay. In QED, well, I can label the legs in the same way, right? And I think there's a well-defined procedure in QED how you can go from this diagram to that in non-relativistic limits. I mean, that's beyond the scope of this course, but I think if you were to assume a situation when electron velocity is much smaller than the speed of light, you could basically integrate out the photon, make it sort of instantaneous, and you would get this type of a diagram. In condensed matter language, what this means is that you're neglecting all the magnetic effects between two electrons. They interact purely as an instantaneous Coulomb interaction. A correction to that would be some magnetic effects which arise from, magnetism is basically a relativistic correction to electricity. Okay, question?
When you put up on the first day when you were talking about the condensed matter theory of everything, and of course it didn't have these relativistic corrections, which made sense. Is there any sort of like evidence or proof that when you look at the macroscopic properties of a solid, if you were to model them down from your condensed matter theory of everything exactly, you'd actually get the right results qualitatively? In other words, is there evidence that there isn't some like creeping up from the corrections due to relativistic corrections?
Okay. So the answer to that is Well, relativistic corrections are creeping in. At this level, we're just not considering them explicitly. The reason is that the typical velocities of electrons in a metal, as we will discuss shortly, are roughly c/100. So they are about 2 orders of magnitude less than the speed of light. So you may expect that all corrections are down by this factor squared. So they are very small compared to these energies. However, all the magnetic effects in solids can be attributed, as I just mentioned, to relativistic corrections. And you know, they are treated. I mean, once you start being interested in magnetic effects that affect spin-orbit coupling, and so on, then you sort of are forced to consider relativistic corrections to this. But typically, they are treated as a kind of a perturbation to these results because they are typically small at these energy scales. Yeah. So in other words, it doesn't really make sense to formulate fully covariant theory of condensed matter just because you know, that becomes complicated, and these corrections that you find are very small. What is traditionally done, you first neglect them, and then you can add them in to leading order in this small parameter. That's how it's usually done.
And it's usually enough to make the ad hoc correction.
Yes, yes, yes. So it's usually, I mean, in all cases that I know of, it's enough to take leading correction. There's never really any need to go beyond the leading correction. Yeah. Okay. So we now went through all this formalism. So let's now reap some benefits finally and learn a little bit about physics that arises from these considerations. So one very nice result can be obtained just by looking at the scaling behavior of this Hamiltonian. And let me just do that. Let me rewrite this Hamiltonian in dimensionless variables. And in order to do that, let's first consider what are the typical length scales that occur in the system so that we can then divide them out. And there are two obvious length scales in the system. Remember, we have a jellium model. We have a bunch of electrons on the positive background. And one typical length scale would be the typical spacing between electrons, right, which we call R0. So and this length scale can be simply obtained by saying that volume per electron is given by a sphere of radius R0, okay? Or if you multiply this equation by n, then basically you get that the total volume of the system is a volume per electron times the number of electrons. And from this, you can back out R0 in terms of electron density. And so you can get that R0 is 3/4 divided by pi density to 1/3. So this is one length scale that one could expect to play some role in the system. And the second important length scale is the Bohr radius. And this comes because, of course, the interaction between electrons is Coulomb. So whenever you have Coulomb interaction, you can form Bohr radius. And this is given as h squared over me squared. It's basically given by the mass of electron and its charge. And we know from elementary physics that this is roughly half an angstrom. Angstrom is 10 to minus 10 meters. Hopefully everybody remembers. And the interesting dimensionless ratio, Rs, is that between these two length scales, R0 over A0. And it turns out that in most simple metals, this ratio happens to be between 2 and 6. And this is an empirical fact. When you measure density of electrons in the sodium metal or aluminum and plug it into that equation and compare it to the Bohr radius here, then for almost all metals, those values fall into this range. And this will be important in what we say next. So what I'm going to do, I'm going to now express all dimensionful quantities in that Hamiltonian in terms of the first length scale, the distance, typical distance between electrons. So I define dimensionless volume and dimensionless momenta like this. So this is my dimensionless volume. And then I define dimensionless momenta by k bar is equal to R0 times k, p bar equals R0 times p, and the same for q. So this is dimensionless momenta. Okay, and this is a bit complicated because these are supposed to be vectors as well as having bar. In the book, they use boldface for vectors, so they don't care. But I'm not going to put both vectors and overbars there. But remember, these are vectors. And so now I can rewrite that Hamiltonian in terms of those dimensionless quantities. And it assumes the following form. So I can pull out a common energy scale, which will be just the Rydberg, the energy of the ground state of the hydrogen atom. Okay, so this is how the Hamiltonian looks in these dimensionless variables. As I mentioned, all the dimensionful variables are up front. This E squared over A0, that's just a Coulomb energy of the hydrogen atom, 13.6 electron volts. It's divided by this dimensionless number Rs squared, and everything else here is dimensionless. And the interesting thing, the reason why I did this for you, is that the two terms, the kinetic energy and the potential energy, have different scaling with this dimensionless variable Rs. Namely, in the limit, when Rs goes to 0, the interaction term becomes unimportant. Okay? And this is our first important result. So Rs very small. Okay, so now okay, so now my mistake has been revealed. So what I was going to say that Rs small corresponds to this R naught being small, and that happens when you're in a limit of high density. And then I looked at that formula and it didn't look like that, and that's because I didn't solve the equation correctly. But now that it's corrected, you can see that when the density is high, since it's here in the denominator, this R naught is small. And so, again, sorry about that mistake. This limit, Rs goes to 0, corresponds to a limit of high density. And in this high density limit, the expression for the Hamiltonian is totally dominated by this first term, just the kinetic energy. And two comments about this. First of all, this is kind of surprising because it's the opposite what your classical intuition might tell you. You would expect that interaction between particles becomes more important as you go to high density, right? When you have very dilute particles, they hardly ever interact, and therefore you may expect quite the opposite. And in this case, it's basically because these are quantum particles and the kinetic energy and the potential energy scale somewhat differently than what you would naively expect. And also, it's a Coulomb interaction, which is long range. And again, this leads to somewhat non-intuitive scaling, but it's been worth to go through this in detail to reveal this property. And second comment is that in this high density limit, if we can neglect this term or just treat it perturbatively, it's a limit where we can solve everything because non-interacting Hamiltonian we can understand. Okay? So once again, this is our first physical result, and I'm happy to get to it in the third class, that interacting electron gas becomes basically non-interacting in the limit of very high density. Any questions about this? So in this limit, one may expect to be able to treat the second term perturbatively and then express physical quantities such as ground state energy as an expansion in this small dimensionless parameter. And one can expand specifically, one can expand the ground state energy in powers of this quantity, and the expansion looks like this. Again, I take out the dimensionful parameters and recognize that the energy will be an extensive quantity. It should scale with the number of particles in the system. And then I expect the behavior to look like this. And here, I expect naively just C times R squared, but it turns out when you do the calculation, there's a more dominant term which has a log. Like this, where A, B, C, and D are just some numerical coefficients. This is all dimensionless. In this class, as an example of how one manipulates with these creation annihilation operators, we're going to explicitly calculate the first two coefficients. Coefficients C and D can be evaluated with just a slightly more effort doing perturbation theory to second order. It gets slightly messy, so I will not go through that in class.
Where does the logarithmic term come from?
Logarithmic term comes from the fact that there is a term in the second order perturbation theory that actually diverges logarithmically, and the way to deal with it is to basically assume some screening in your Coulomb interaction, which basically corresponds to a resummation of some divergent diagrams in the perturbation theory.
This is like some kind of a cheat because we have to just neglect it.
Yeah. So if you were to just calculate this second order perturbation theory straight without any thinking, then you would find that it diverges. But it can be cured by considering that this interaction will be screened. And screening is something that we will discuss starting tomorrow. But anyway, this expansion can be found in the literature carried up, I think, up to 7th order. But anything beyond second order becomes quite messy, and you don't want to do it by hand. There's these computer programs that allow you to resum the diagrams and so on. But anyway, as an example of how we deal with these things, we now derive these coefficients A and B. Okay? Any questions before we start this? Yes?
Under sort of what conditions does this limit, as in like, what kind of metals does this apply to, that this high density limit?
So like I said, in real metals that we find in nature, this parameter is 2 to 6. The question is this sufficiently close to 0 to permit this expansion? It turns out that it is. And it's not obvious why, but kind of a more in-depth analysis of this turns out that this is actually not bad for regular metals. And we will see some signature of that in a moment. This is not a rigorous analysis, but there's some results that are suggestive that this expansion actually, even to low order, can be applied to simple metals.
Isn't that divergent series? That's not less than 1.
Say it again?
We're expanding it, assuming RS is less than 1. So
Well,
that series went.
we're expanding it, assuming that RS is small. But of course, what is the radius of convergence of this series? That depends on how these constants behave, right? If they have 1 over n factorial in them, then the radius could be infinite, right? And it turns out that when you evaluate these coefficients, when RS is in this range, the expansion is kind of okay. Yeah. Any other questions? Okay, so let's get to it. So what we will do, we will now evaluate these first two coefficients, and basically we will proceed as in perturbation theory. We get back to the original Hamiltonian, and we treat its first term as H naught and the second term as H prime in standard perturbation theory, and see how this works. So we do perturbative expansion, and we take H naught to be sum over k lambda, H bar squared k squared over 2m, C dagger k lambda, C k lambda, and H1, the rest of it, E squared over 2v, sum k pq, alpha beta, 4 pi over q squared, C dagger k plus q alpha p minus Q beta, C P beta, C K alpha, and do the standard perturbation theory on this. And what we want to calculate is the ground state energy. Okay, so remember perturbation theory, everybody remembers that. So first step is we need to find what the ground state of this Hamiltonian is. So what is it?
You occupy a certain number of electrons.
Yes. So remember the way we construct the ground state of this single particle Hamiltonian, we have some number of electrons, and we start putting them in the lowest energy states that are available, starting at k equals 0. That's obviously the lowest energy state, and then increasing with momenta up to the point where we fill in, where we expend all our electrons, and that forms a Fermi sphere. So pictorially, we have momenta, kx, ky, and we start filling in. And ultimately, we fill in some sphere in momentum space whose radius will be the Fermi energy. And in symbols, we can write this Fermi sphere ground state as a product of k less than kf, c dagger k up, c dagger k down, acting on a vacuum state, where vacuum state is defined as a state with no electrons. Okay, so this is the formal expression of the Fermi sphere. And we can easily calculate the energy of the Fermi sphere. But before we do that, let's just calculate the number of electrons that fit in for a given value of kf. That's an important relation between kf and the density that we'll need in the following. So number of electrons in the Fermi sphere is just the expectation value of the number operator in that state. And one can do this the hard way, basically take the number operator, plug it in, and just do the commutation relations. And if you've never done such a thing, then I recommend that maybe you do that as an exercise. But often one can do these things by inspection. So the number operator acting on the Fermi sphere, this can be written as follows. We write the number operator as sum over k and lambda f n k lambda. This is the number operator acting on a given state. And now all that one needs to remember is that this operator gives you 1 when the state is occupied, namely when the momentum is inside this Fermi sphere, and it gives you 0 when the state is empty. So what this ends up being equal to is just sum over k and lambda of a step function kf minus k. Theta is just a step function. Theta x is equal to 1 when x is greater than 0, and 0 when x is less than 0. Okay, so that just expresses what I just said in words. And what we now want to do, we want to, in thermodynamic limit, we want to express this summation through an integral. And the rule for that is the following. And again, I hope you've seen this in undergraduate solid state physics. Okay? So in thermodynamic limit, we can replace 1 over volume times this momentum integral with an integral over infinite space with this volume element. One way to remember this is just through dimensional analysis. This k has a dimension of inverse length, so you need, so that they have the same dimension, you need this volume on the left-hand side to make them the same. Sometimes we will abbreviate this integral like this, just so that we save writing. So this in thermodynamic limit can then be written as v over 2 pi cubed times sum over 2 spin projections d3k of theta kf minus k. So it's an integral just of volume up to a radius kf, which is nothing but the volume of a sphere, right? And let me just continue here. So I can rewrite this as v over 3 pi squared times kf cubed, where I just cancel the various factors. So I would get 4/3 pi kf cubed for volume of the sphere, and then I cancel some of these factors. And also, since this is independent of spin, I get another factor of 2 from summation over 2 independent projections of spin. And now I look at the beginning and the end of my equation, and I can express kf through the density. So from here, I get an expression for kf, my Fermi momentum, as 3 pi squared n over v to 1/3. And one can write this in a number of different ways. For instance, one can express this in terms of this length between a typical length scale, distance between particles, as 9 pi over 4 to power 1/3 times r naught minus 1. And again, on dimensional grounds, this makes sense because momentum is inverse length scale, so that's borne out here. Okay, so this is again, I put a little box around this. This is an important relation between Fermi momentum and particle density in 3 dimensions. I think you derived something like this yesterday in your tutorial in 2 dimensions, and there the power here would be different, but otherwise the relation is similar in the spirit. Okay, any questions about this? So the next step, remember, we were evaluating the ground state energy in this perturbative expansion. So let's do that, and I will proceed pretty quickly because everything goes along the same lines. So similarly, the energy to 0th order is simply the expectation value of h naught in this Fermi sphere. And this can be rewritten once again as sum over k lambda h bar squared k squared over 2m f n k lambda f, where I'm simply putting in the explicit form of my h naught and recognizing that this I can pull out of the expectation value, and also recognizing that this is nothing but a number operator. So we see that this sum is actually very similar to this sum, except that I have this k squared term. So I can just do everything in precisely the same way and write it in terms of this step function, then convert into an integral. And it's an elementary integral that looks like this, h bar squared over 2m, sum over lambda v over 2 pi cubed. And I have integral d3k, but now I have k squared times theta kf minus k. So this is basically an integral in this momentum space of k squared times this volume element up to kf. And I can simply evaluate that, and the result is this, 3/5 h bar squared kf squared over 2m times n. I recognize this combination as the Fermi energy. Okay. Which is defined as the energy of the most energetic electron right at the Fermi surface. And this can therefore be written as 3/5 times EF times N. So this is an interesting result in the non-interacting, well known for non-interacting electron gas, that the total ground state energy of the system per particle is just 3/5 of the Fermi energy, which is the energy of the most energetic electron in the system. And there's another way in which I can rewrite that, which is also useful. This is going to be useful when we plug it back into that expansion. And it looks like this. So this is E squared over 2A naught. 3/5 9 pi over 4 to 1/3 n divided by rs squared. And if I evaluate these various constants, I can also write it as 2.21 E squared over 2A naught n over rs squared. Okay, any questions about this? So let me proceed to evaluating okay. Let me just make one more point, and then I go to the second order. So the point that I wanted to make is that this combination here is often known as the Rydberg. E squared over 2A naught is 13.6 electron volts, which is the binding energy of the hydrogen atom. So we will, again, use that in the following. But let's proceed to the first order, second order perturbation theory. And here, sorry. Yeah, I'm just, I was right. So this is the first order perturbation theory. What we calculated before was the 0th order energy. And this is the first order perturbation theory. And the general recipe tells us that we have to evaluate the expectation value of our perturbation in this ground state. Now, this is going to be slightly more tricky than these previous evaluations, so let's do that in some detail. Let's write this in terms of the creation annihilation operators. Okay, so now we're evaluating this type of more complicated expression. And again, one can do this the hard way by just plugging in this definition and then trying to do all the commutators manually. That's messy, and this is much easier done in kind of by a simple argument. So basically what happens is that I first hit my ground state Fermi sphere with two annihilation operators, right? So here's my Fermi sphere. And my filled states are inside this sphere. So first of all, in order for this to be non-zero, both P and K have to be somewhere inside this Fermi sphere. If either one of them is outside, then this just hits a vacuum and gives me 0, so I don't have to worry about that. And the second consideration is the following. Then I'm going to create two of the electrons. But the only way that this whole expectation value is non-zero when these two operators are precisely such that when they act on this Fermi sphere, I get back the same Fermi sphere as before. Because if I get some other state, then it will be orthogonal to my Fermi sphere, and I will get 0 again. Okay, so basically the only way this is going to be non-zero is when these two guys annihilate two electrons in the Fermi sphere, and these two guys just create them back. Okay, and there's two ways this can happen. It can either happen when this creation operator fills the hole that this one has created, and this one fills the hole that the other one has created, or it can happen the other way around, like this and like that. And if you studied Wick's theorem, this is basically a kind of poor man's derivation of the Wick's theorem, but it's nevertheless a very powerful argument here. Okay, so again, by this argument, this expectation value will be non-zero if two possibilities, two conditions are satisfied. Either K plus Q and alpha are equal to K and alpha, and P minus Q beta is equal to P beta. So this is one possibility which represents this upper pairing. And this is called a direct term. Or this can be non-zero when this possibility indicating down here is satisfied, namely when K plus Q alpha is equal to P beta, and P minus Q beta is equal to K and alpha. And this is called the exchange term. Well, basically because the two electrons here have exchanged. Question?
Just a minor thing. When you did the contractions on the bottom, you didn't draw them properly.
I didn't what?
You didn't draw the parents on the bottom properly.
Ah, yes. Very good. Yeah. So I have to contract. Sure. Yeah. Thank you. It should go like this. Okay. Thank you. That's a very good point. Okay. So any other questions about this? Okay, so the next thing that I note is that this first possibility, direct term, implies that Q must be 0, right? Because K plus Q must be equal to K, which only is possible when Q is 0. But this instruction here for Coulomb interaction instructs us to omit that term from the summation. So direct term, in this case, does not contribute. Although for some other interaction, if the prime was not there, direct term would contribute. So the only thing that actually contributes in this case is exchange. And let's evaluate that, because that is non-zero. So let me just write the matrix element, and I will use these conditions to evaluate it. Now notice that they are in fact just a single condition, because for spin it just tells me that alpha is equal to beta, and for momentum it tells me that K plus Q is equal to P, and the second equation is equivalent. So there's just one condition, and therefore I can write this matrix element as follows: delta K plus Q P delta alpha beta. And here I have my matrix element F. And it's the same thing. So let me not copy that. So imagine I just put it in there. But the point is, what I'm going to do, so it's this lower pairing. And once again, when K plus Q is equal to P, then what I want to do, I want to use commutation relation to exchange these two guys, right? And then these two will just form a number operator, and these two will also just form a number operator. Furthermore, since Q must be non-zero, I don't get any extra terms from this anti-commutator, because P and P minus Q can never be the same. So that immediately simplifies this expression, and it looks like this: minus K plus Q P delta alpha beta. And I just have a number operator here: N K plus Q alpha and K beta F. And now everything is similar to the evaluation previously, because once again, this N, when it acts on the Fermi sphere, either gives me 0 or 1, depending on whether state is occupied or empty. So I can now immediately proceed to write my first order perturbation theory energy. And it's minus E squared over 2V, sum over alpha, sum over KQ prime, 4 pi over Q squared. And now I have two step functions, Kf minus K plus Q, and theta Kf minus K. Okay? And again, in thermodynamic limit, I rewrite this in terms of integrals and obtain the following. Like this. And the rest is a somewhat tedious evaluation of this integral. So let me just outline how this is done, but I don't want to spend way too much time on this. Basically, I want to define new variables. I want to change k to a new momentum variable, capital P, that is defined as k plus 1/2 q. And in these new variables, this E1 becomes minus 4 pi e squared v over 2 pi to power 6 integral d3q 1 over q squared integral d3 capital P. And now the integrand looks more symmetric. That's the advantage of this. Okay. So yeah, the advantage is that I can now evaluate this integral separately, and it's kind of symmetric. If you think about this for a moment, this integral has a geometric interpretation of two spheres in momentum space, and we're calculating the overlap of these two spheres. So basically, there are two spheres in momentum space whose centers are displaced by q. And the product of these theta functions means that it's only non-zero when these two spheres overlap. Okay? I mean, each of these guys represents a sphere. Basically, it's non-zero inside the sphere, so the product will only be non-zero when the spheres overlap. And this is an exercise in three-dimensional geometry to calculate such an overlap. I will not really engage in that exercise other than stating the result here that once you calculate that integral, what's left is 4 pi e squared v divided by, again, 2 pi to power 6. And then you get 4/3 pi kf cubed. This is the sphere that you get. And then you get 2 kf times integral from 0 to 1 dx 4 pi 1 minus 3/2 x plus 1/2 x cubed. And I have defined a new variable here that is q over 2kf. So basically, this is the volume of this overlap region. And you can see that it goes to 0 when x goes to 1, meaning when these spheres just touch, it goes to 0. So that's fine. And this is an elementary integral that can be evaluated. So let me just give you the answer here. It's minus e squared over 2a naught n over rs 9 pi over 4 to 1/3 3 over 2 pi. And if one evaluates these various constants, this can be expressed as minus 0.916 e squared over 2a naught times n over rs. Okay. somebody already did it for us. Interesting. Okay, so after this somewhat tedious calculation, let's just put everything together. So we calculated this energy in zeroth and first order perturbation theory. So let's just combine the two results. E0 plus E1 is equal to, and I want to divide this by n. So this is energy per particle, E squared over 2A naught, 2.21 divided by RS squared minus 0.916 divided by RS. And then there would be additional terms coming from higher order perturbative expansion. And let me just note here that this is RS small, AG high density. So this expansion is valid in the limit of high density. Okay, any questions about this calculation? So let me now kind of turn the cards on you a little bit. So we view this as a perturbative expansion. And as such, it can be expanded to higher order. We will not pursue that. If anybody's interested, I can point you to some resources where this is done. But one can equally well view this as a variational calculation, right? Because all we did, we just calculated at this point, what we did, we calculated this EG as being an expectation value of our Hamiltonian, both kinetic and potential energy, in a particular ground state, right? That we chose to be the Fermi sphere. So this can be viewed as a variational calculation. With density, or equivalently RS, as a parameter. Okay? It's an equally valid point of view. Remember, in variational calculation, you take a Hamiltonian that you don't know how to solve, but you calculate the expectation value of that Hamiltonian in some ground state that you postulate, and it is guaranteed to give you energy higher than the true ground state of the system. So if that wave function has some parameters, what you can further do, you can optimize your energy by varying those parameters and finding the minimum. And that will be your best variational estimate for the ground state of that system. So let's do it here, right? So if we view this as a variational calculation and RS is our parameter, then we can try to find what value of this RS minimizes this energy, and that will then be the best estimate for the ground state. So let's just do that. Let's plot this EG calculated in this fashion as a function of RS. And it's a function, and this is EG. We're plotting EG per particle again to get a finite result. And it looks something like this. So if I were to plot this function, it just looks like this. The scale roughly here is 0.1 in units of this energy scale, 13.6 electron volts. This would be roughly minus 0.1. This would be 2, 4, 6, 8, and so on. And we see that there is a minimum here, which one can simply calculate. It's related to these two coefficients. And it turns out that this minimum, Rs at the minimum, is 4.83. And one can similarly calculate the energy at that minimum. So let me call this Rs at the minimum. And similarly, I can call this Ag over N minimum. So this value is minus 0.095 of this E squared over 2A0, or approximately minus 1.29 electron volts when I put 13.6 electron volts for this value. And this is quite interesting because, first of all, this value here falls right in the range of this, where is it, 2 to 6 in simple metals, right? And one can compare this, for instance, to measured values for sodium metal. This is one of the simplest metals. For sodium metal, Rs is measured to be 3.96, and Eg over N is measured to be minus 1.13 electron volt. So in the simplest metal, which has just one conduction electron, and really, if you measure, it has nice parabolic band dispersion, this works quite well. Okay. Now, this is not to overstate the accuracy of this method. It's a very crude method. Plenty of things are neglected. However, this, I mean, if I would get this minimum to be 0.01, then it would be a huge discrepancy from actual materials, and I would conclude that this method is crap. If it comes within the acceptable range, then I can conclude that at least as a starting point, this is not such a bad approximation. Any questions? Okay, let me just remark one more thing, just for your information. I will not go into any details, but so we discussed high density limit. One can also similarly treat low density limit. Which is Rs goes to infinity. In that case, you can see that it's the second term that dominates, right? This one is small. And one can do a similar thing. One can expand around the ground state of this term, which is a so-called Wigner crystal. So this has been discussed back in the 60s by Wigner. Who basically showed that in the limit of low density of this problem, when Rs goes to infinity, electrons are actually expected to crystallize, which is kind of interesting. And one can perform a similar expansion, but now treating this as H0 and this as a perturbation. And basically what happens is that you have a crystal at Rs go to infinity, and as you turn on the kinetic energy, the crystal starts vibrating, and ultimately, presumably, it melts. But at that point, your expansion becomes invalid. And in that case, you can do this expansion from the other side, and it becomes, it looks like this, E squared over 2A0. So this is low density. And if you were to plot this on a plot like this, then the line would look something like this. So, basically they converge in this region here. This line would then diverge at minus as the density grows, but basically in this region those two lines kind of meet, and so you may expect that this is a kind of reasonable approximation. Any questions about this? So the next topic that I want to address is Hartree-Fock approximation and screening. Now I'm basically out of time. I started about 10 minutes late, but it's probably too late to start a new topic because it would take me at least half an hour to make some progress. But nevertheless, before I adjourn, let me ask you to do a little bit of reading for the next lecture. This is something that, again, should be viewed as a part of undergraduate background, something that you might have seen in electricity and magnetism or in a condensed matter course. It's just a basic discussion of screening that defines dielectric constant and susceptibility. And I don't want to spend half an hour in class kind of reviewing that because you might have seen that and it's a simple material. So I ask you to just read 2 pages from Ashcroft and Mermin so that we can use that without me having to spend time on it. And it's a section called Screening General, meaning it's basically a bunch of definitions, and it's Ashcroft and Mermin, pages 337 through 339. So it's basically 2 pages and few lines. And I just want you to read it and understand the final result. How is dielectric constant and susceptibility related to one another, and what they mean for the electrical potential in a solid. Okay, are there any questions about any of the material today? If not, then again, thank you for your attention, and I see you tomorrow.